The Zoom session is being brought to you by the fractal Swirly 3 Horizon S. All right. Okay, let's get to this. Well, okay, we've covered through the end of chapter 5, and I've opened up the final, and I believe we already, and quiz 2 is open. Everything is open. You have till the 25th to get everything done. Please try and get things in a little bit before the 25th. And in any case, in the last week or so, I will not be giving out, not be sending you what to correct. I'll just simply give you the grade back and so on. So there's that. Let's see. And well, okay, we have a little time these 2 days this week, and I said 26th, not 25th. This week and next, I'll be covering. Well, I think I should cover some of this extra credit stuff. So last time I covered this, I mentioned the hourly trigonometry. Connected to it, I forgot to mention this, just connected to it, and that's this fill up this trig table. And the idea is to fill in values of sine, cosine, and tangent. Why is it off the edge there? And for these multiples of 15 degrees, 0, 15, 30, 45, 60, 75, all the way on up to 285 degrees, all the way around the circle. So 21 point per row and 24 points in all, and exact values. So instead of 1.414, it should be square root of 2 or what have you. I allow pi's and when we're dealing with radians and so on. Okay, so there's that. In addition, okay, why is this being like this? Okay, whatever. All right, let's look at various things. Okay, so in addition to this, tell you what, I'm going to go over this, the pendulum rule. This is for the side-side angle problem. Often called angle side-side, but I decided not to call it that for very 10-year-old reasons. But it's also called the ambiguous case. Now, okay, side-side angle is covered by the law of sines, but there are other ways. So here we go. So here we have a triangle. We have we're given the side, a side, and the angle. Find the other side and the other two angles. We're given alpha, B, and A. Find C, beta, and gamma. So, okay, this can have 0, 1, or 2 solutions. If A is less than B sine alpha, then basically, I think of this, I call this the pendulum rule because I think of this as a pendulum at the end of a cantilever. And if the cantilever is too high up and the pendulum too short, then it doesn't touch the ground at all and there's no solution. If A equals B sine alpha, then this angle is low enough that this touches the ground at one spot and only one spot at right angles, and we get one solution. If B sine alpha is less than A and B, then the pendulum touches ground 2 places. So there are 2 solutions. And there's a third case. There's another case where if B, the length of the pendulum, is bigger than A, the length of the cantilever, then of these 2 solutions, one of them involves going backwards, the pendulum reaching out behind for a negative angle of a value of an angle, not acceptable. And so we say that there's just this one solution. Because of these different numbers of solutions, we call it the ambiguous case. And here's one way to look at it. Start out with the pendulum at the end of a cantilever at angle alpha. Now let's drop this perpendicular here of length F, right angles here, and because these are equal in size, so are these symmetrical. So these 2 lengths E are the same. And this distance out to the base here between where the pendulum touches down, call that distance D. Call the distance down to the first place the pendulum touches down, call that C. Call this other distance, call that C. So find C. Well, here's the thing. C is D, this length, plus or minus E, this length. Now D is B cosine alpha, that comes straight from right angle trigonometry. So C is B cos alpha plus or minus E. Now what's E? Well, E squared plus F squared equals A squared. And F, it's a perpendicular here in this right triangle. F over B equals sine alpha. So F equals B sine alpha. So E squared plus B squared sine squared alpha equals A squared from here. So E squared is A squared minus B squared sine X squared alpha. And so E is the square root of A squared minus B squared sine squared alpha. Now remember, C is B cos alpha plus or minus E, namely this. So you put it together and get C equals B cosine alpha plus or minus the square root of A squared minus B squared sine squared alpha. I call this the pendulum law. Its main difficulty is that unlike the sine law and the cosine law, it's not terribly symmetrical. So it is what it is. Now, okay, given two sides, A and B, and the angle alpha, side angle, this will give you C, the third side. And then from all three sides, use the arc sine law, their cosine law to find the other two angles. All right, so here's how we do this. But here's what we'll do. From this pendulum law, we can we'll use this to derive the law of cosines. Simple enough. From here, we subtract B cos alpha from both sides. So C minus B cosine alpha equals plus minus root A squared minus B squared sine squared alpha. Now square both sides and the square root sign goes away and we have C minus B cos alpha all squared equals A squared minus B squared sine squared alpha. Now we expand this side. C squared minus 2CB cos alpha plus B squared cos squared equals A squared minus B squared sine squared. Very good. Transpose the B squared sine squared to the left by adding it to both sides. And when you do that, here we have a B squared cos squared alpha plus B squared sine squared alpha. That's just going to be B squared times cos squared plus sine squared, but that equals 1. Therefore, you get C squared minus 2BC CB cos alpha plus B squared equals A squared. And this is the law of cosines. We've seen it elsewhere. Here we derived it. So given side angle side, you can find all three sides as well as the angle. And all right, now, and then from here, from the law of cosines, you solve for cosine. Cos alpha is B squared plus C squared minus A squared over 2BC. So alpha is inverse cosine of B squared plus C squared minus A squared over 2BC. That's the law of arc cosines, which given three sides gives you all three angles. Now there's a rule I call I've made up a name for it. I call it triality. The idea is that there's a threefold symmetry of the laws of triangles. You have a trigonometric identity, and it remains valid if you swap all the letters, A to B to C to A, alpha to beta to gamma to alpha. The idea being, so here's what triangle labeled up, and here we label the same triangle with different letters. Same triangle, labels differ. So the trigonometric identities have to be symmetrical in the same way. So by swapping around A, B, C, alpha, beta, gamma, you can, starting with this, the pendulum law, you can swap it around to get a pendulum law for B and one for a C. So B is A cos gamma plus or minus C squared minus A squared sine squared and gamma. C is B cos alpha plus or minus A squared minus B squared sine squared alpha, what have you. And from this law of arc cosines, if you swap them around, you get law of arc cosines for B and C. B is root C squared plus A squared minus 2CA cos beta, and C squared is A squared plus B squared minus 2BC cos gamma. And that's the law of cosines. Law of arc cosines, again, swap around. Here's a formula for alpha, here's one for beta, here's one for gamma. And of course, if you have two angles, you get the third by subtracting the result from 180. So for example, you have a triangle with 31 degrees here. This is length 1, this is length 2. What is C, gamma, and beta? Well, C is B cos alpha plus or minus A squared minus B squared sine squared alpha. That's the formula. Plug in 31 degrees for alpha, 2 for B, 1 for A, and after a bit of work, it's 1.7143 plus or minus the square root of a negative number. But square roots of negative numbers are complex, and we don't have complex triangles. So there's no real solutions to this problem. alpha is too high, so the pendulum A swings back and forth and misses the ground entirely. Here we have alpha is 30 degrees, A is 1, B is 2, what's C, gamma, and beta? All right, if you work it out, C is 2 cos 30 plus or minus 1 minus 4 sine of squared 30, which comes to root 3 plus or minus root 0, which is root 3, a single solution. This is a single solution case. If you calculate gamma, it's going to be arc cosine of 1 squared plus 2 squared, those are A and B, minus root 3 squared, that's the cosine. 2 cos 30, and square that, excuse me, over 2 times 1 times 2. And this works out to arc cosine of 2/4, which is 60 degrees. For beta, we subtract alpha and gamma from 180, get 90 degrees. So we had actually getting a 30, 60, 90 triangle. C is root 3, gamma is 60, beta is 90. If we have alpha is 29 degrees rather than 3 degrees, 30 degrees. And these are sides 1 and 2. All right. Here, alpha was 31, the pendulum missed the ground. Here, alpha is 30, the pendulum hits the ground at 1 value. Here, alpha is a little bit smaller. And let's see what happens. Well, we'll get 2 places. C is 2 cos 31 degrees plus or minus 1 minus 4 sine squared 29 degrees minus 4 sine squared 29 degrees, which comes out to about 1.749239 plus or minus 0.244619. So there's 2 solutions to it. Okay, here's one solution, 1.749 minus 2.44. This 1.504620, or this, which is 1.749239 plus 2.44619. Namely this, C is 1.993858. To find the gamma, we use gamma's arc cosine of A squared plus B squared minus C squared over 2AB here and here. After a bit of work, gamma is 46.84 in this case and 75.16 in this case. Having gotten that far, we can find beta by subtracting 29 and gamma from 180. 29 and gamma from 180. And here you get beta is 104.16 degrees. Here beta is 75.840 degrees. So we have 2 triangles. One is C is 1.5046, gamma is 46.84, beta is 104.16. And here, where gamma is, where C is 1.993858, gamma is 375.16, and beta is 75.84. 2 solutions. Okay, here I have a list of problems, 8 problems or 8 points. Notice I have a dotted line down here, down the middle. So that if there's 2 solutions, you can write 1 solution here and the other solution here. There could be just 1 solution, just write that. Or it could be no solutions and just write that there. So that's how it works. Okay. Okay, that covers the pendulum. Let's see. Next time I'll cover the stereo and free height, maybe. So, okay. All right, so I think that'll do for now.